We have here a comic to illustrate the meaning of a confidence level, such as 95% confidence. In the first pane, we see the words, "I'm pretty sure that it won't go above freezing today," which we could take as low confidence. Of course, Snowman says, well, I need to be really sure. But given that she has only the same amount of information that she's basing her statement on, she says, okay, if I have to be really sure, which is high confidence, we can see that what we get out of this is somewhat useless information, right? That the temperature will be somewhere between 40 below zero and 200 above. So thinking about these mathematically in the context of confidence intervals, pretty sure the temperature won't go above freezing means perhaps she's thinking it will be somewhere between, let's say, 0 and 32 degrees. The 0, of course, is not necessarily implied here. This actually could be any lower bound. And when she makes the statement again with high confidence, we see that that interval goes from negative 40 to positive 200. So this is a much wider interval. You could even think of this as a 100% confidence, so maybe the pretty sure was something like 75% confidence, and the really sure is 100% confidence. This illustrates a couple of things for us. One thing that it illustrates is that, of course, our interval got wider when we went up from 75% confidence to 100% confidence. If we want to be sure that we're correct, then we have to allow for more numbers to be in our interval. The other thing this illustrates is why we're not interested in 100% confidence intervals. We always have some confidence level that is below 100% because if we want to be certain, we have to go all the way out to the natural bounds of the situation, and we generally don't get useful information that way. So this 100% confidence interval is not useful information. The reason that we need to allow for some chance of being wrong in statistics is so that we can narrow in on an estimate and actually provide a useful estimate of something. And so the success rate, we could call this a success rate, is what we think of that confidence level as meaning. What this means in this context is that if she were to estimate an interval for the temperature on 100 different days, then if we have 75% confidence, we think that 75% of the time she would be right. If we have 100% confidence, that means that 100% of the time she would be right. And we can see how easy it is to get 100% confidence with this very, very wide interval where it's almost impossible. Certainly here in Austin, it is impossible for that to come out to be wrong. So in this context, we could say that the confidence level of these estimates is if we were to take all of the temperature estimates made by this person, assuming that the same methodology is used each time, that it's based on the same way of gathering information and making a prediction, then whatever percent turn out to be correct should be the confidence level for this method of estimation. Now, one difference between this situation and most of the situations we see is that this one is predicting a day in advance. We find out pretty quickly whether it was correct or not. Most of our estimation is of things that we never really know the true answer for. Like, for example, if we're trying to estimate presidential approval rating, we come up with a confidence interval. We might say it is 42%, give or take a 3% margin of error. We never find out what the actual approval rating was in that moment. We just keep going and we keep coming up with new estimates in the future. It remains an estimate forever. So that success rate is usually something that we can't verify empirically. It's something that we just accept as a result of the methodology that we are using. So this image that we have here under the StatKey tutorial shows repeated sampling, and for each of those repeated samples getting a confidence interval. So using some calculation for the margin of error, and then you can see that each of these intervals would then be centered at the sample statistic. We can see that only one of these is a little bit off, and what this is intended to illustrate is, here we're talking about a sampling distribution for a mean. This bar in the center represents the population mean mu. So each of these intervals is centered at some sample mean x bar, and the margin of error gives us an interval. So an x bar along with a margin of error gives us an interval. Now in this case we have 20 independent samples, and therefore we have 20 different confidence intervals. And we can see that one of those 20 doesn't include the population mean mu, right? 1 out of 20 is in fact 5%. So that is the 5% that was wrong. Now looking at this image, we know which one was wrong because in this case, as we'll see when we go through the tutorial, we're looking at a data set for which we have the whole population. We know the population mean, and we're just generating these confidence intervals for illustrative purposes. Most of the time that we're generating a confidence interval, we don't know that parameter that we're trying to estimate. But let's go ahead and get into this tutorial and see how you can generate a graph that looks like this one. So here in StatKey, we're going to go to sampling distributions for a mean. So we'll start here. And just because the data set doesn't particularly matter for these illustrative purposes, we'll go ahead and accept the default data set of % with internet access and the default sample size of n equals 10. And we're going to generate 20 samples, so I'll just hit the generate 10 samples button twice. And over here where we see the word population and we have a graph of our original population, notice that there's also two tabs above it. One says data plots, which is where we are right now. Click on the one that says confidence intervals, and you'll see that for each of the samples we just generated, we now have a confidence interval. If all of yours are green and cross that center line, then go ahead and just reset your plot and start over so that you at least get one or maybe two that miss. And I got one, which is the exact expected number to get from 20 samples, because that's 5% of 20. And in my case, that is at 64. It's centered at 64.350. I can see that when I hover over this, a dot on my dot plot right above 65 here also seems to illuminate a little bit. And it's not too surprising that the one that misses corresponds to one of the more extreme values in the plot. So generally either your highest or your lowest values in your dot plot are going to be the ones that also get you a confidence interval that might miss. It's just one of those cases where by luck of the draw or random chance, you ended up with a sample that was not very representative, that ended up having kind of a lot of large values in it or kind of a lot of smaller values in it. We can also see under coverage up here that it says 19 out of 20 is 95%. So the 95% confidence intervals actually got us exactly 95% in this case. But if we reset the plot and try it again, this time, oh, okay, I had 3 of them miss. What a good lucky draw here. So this time my actual coverage is 85%. So even within our random variation, there is some random variation, right? We're not going to see 95% every single time. Sometimes it'll come out a little below. Maybe we'll be really lucky and this next time it'll come out a little above. How about that? 100% this time, right? So it's not always going to be exactly 95%, but on average you expect it to come out to be 95% coverage, meaning that 95% of those intervals were correct in that they did include the true population mean, mu here, which is known to be, if we look back at our population, the mean is known to be 43.024 in this case. And that's why it is that we're able to tell which of these confidence intervals are correct and which are not.